My name is Nezih, Yiğitbaşı, and I'm a senior software engineer in the big data platform team at Netflix in Silicon Valley. And today I'm gonna talk about our terabyte scale big data platform that's running 100% on Amazon Web Services Cloud. And so I want to start with a quick survey here. So how many of you guys here have any idea about what kind of technologies Netflix is working on? You know, all of our tech blog, our talks, you know, those kind of stuff. Anyone following your work here? Okay, not bad. So what we are doing is our main business is, so we are streaming content over the internet, you know, all these exclusive content that we build, like House of Cards, Orange is the New Black, you know, those kind of stuff. And previously we were just mailing DVDs around, and then when the internet era, with the internet era, the internet got powerful, the end host got powerful, and then we just started serving the content over the internet. So today I will not talk about the streaming part of it, but I will mostly speak about the big data platform part, the data processing part of the platform. And Netflix is a data-driven company. So whatever decision we take, like whether it's a business decision or it's a technical decision, you know, all this stuff, we just run experiments, collect data, and then do statistical analysis on top of it, and then take a good decision. And today I will just give a few examples of how we use data, the use cases that we have, and hopefully convince in these examples that big data platform that we have built is a centerpiece of that decision-making process. So here is one example. So this is the screenshot of a web application called Ignite. So this is an A/B testing tool. So what our engineers do is, like, if, for example, they want to make a change in the Netflix.com web UI, they just run some A/B tests. So for a group, they show the original Netflix web UI, and for another experiment group, they show the web UI with the change. They run experiments, they collect the data, and they check some performance metrics like streaming hours or retention, and then say like whether the change is good or bad. And this UI just shows the results of the A/B tests that our engineers do. And the back end of this web application is powered by our systems. In particular, it's the Presto distributed SQL engine that powers the back end. I will talk about Presto shortly today. And here's another example. And this is the Netflix.com web page, the main page when you point your browser at it. And what this shows is like all these nice movies that we offer, nice content. And the first part where data is used is the recommendation algorithm. So whenever you log in, you get some personalized recommendations. And those recommendation algorithms are just machine learning algorithms. And those algorithms are trained on our infrastructure using Apache Spark or Hive, you know, those kind of distributed compute engines. And that's one part of the story. The other part is the order of these movies within a row and across rows is also determined by some ranking algorithm. And that ranking algorithm, part of that ranking pipeline, is also running as an Apache Spark job in our distributed infrastructure in the big data platform. And there are many other examples. These are just some of the interesting user-facing examples. And there are many other parts of the infrastructure that depend on the big data platform services. So our biggest challenge is scale. We have a massively distributed system to serve a lot of subscribers that we have. And in fact, we just went global at the beginning of this year. So we are serving more than 190 countries in the world right now. And we have like more than 80 million subscribers just streaming content like crazy. We have 120 million hours streamed per day. And we are supporting more than 1,000 devices, like mobile devices, tablets, phones, game consoles, you know, all these set-top boxes. So we have a wide range of devices that we support. And there's this platform part of it, of the scale too. Like we are pushing to our data pipeline like 100 billion events a day. And then that's eventually demultiplexed, gets written to the 40 petabyte data warehouse that we have, Hive data warehouse, which is stored on Amazon Simple Storage Service, the S3 system. And then daily, we read like 3 petabytes of data per day, and then we process it with all the tools, all the logic that we want to do, and then we write like 300 terabytes a day back to S3. So these are some of the metrics that show the scale of our infrastructure. So let's get a little bit technical, and then I would like to give a glimpse of how our data pipeline looks like. So this really shows where the data come from. So we have two data pipelines right now. One is the event data pipeline on the top, and the dimension data, the subscriber data pipeline at the bottom. So the event data pipeline usually runs under a minute, runs around a minute. And the data is just collected from all the cloud applications that we run on the Amazon Web Services cloud. And these applications may be user-facing or not. Those may be microservices. We just collect data from the users. Like, for example, if you go to Netflix.com and do a search or stream a movie, stop it, whatever, all these events are collected from the cloud apps and then pushed through our Kafka clusters and then sent to Ursula, which is an open source system that we built in the big data platform team. And then Ursula just demultiplexes those events and writes them to S3 eventually. And the bottom pipeline is a dimension data pipeline, which runs daily, every 24 hours. What we do is like, we have a MapReduce job that gets the subscriber data from Cassandra database. That's our online database facing our customers. And then the MapReduce job gets the data, processes it into some format, does some conversion, does some analytics on top of it, and dumps it to S3. And after this part, our platform kicks in, really. So because after this point, what happens is our engineers at Netflix can just use the tools that we built, can use the systems that we built to process these data. So as I said, everything is on S3. It's 100% S3. All the data is on S3 in Apache Parquet format. So I will talk about Parquet today. It's a binary columnar format. So on top of that, we have a number of compute engines. All these are distributed compute engines. They're all open source, like Spark, Hive, Presto, which is a SQL engine. Pig is an old it's an old engine that supports some Pig Latin declarative language, and Druid for interactive processing. And on top of that, we build a number of high-level services to open up unified, easy-to-use interfaces to our internal users. And Genie is a federated execution service that we built, and I will briefly talk about it today, how it allows us to build, to support multiple Spark versions in our infrastructure. And Metacat is a distributed, federated metadata service. So every data has some corresponding metadata. Like, think about it as a schema of your table. So you need to get this schema from somewhere when you do the processing. So Metacat is doing that. It's not open source, but it will be open source soon. And we have a number of tools built on top for ease of access and ease of use of these services, like Forklift for transport, visualization, quality, or performance visualization, monitoring, all this stuff. We have a number of tools that really gives a lot of visibility and ease of use to all this complex machinery. And on top is a one-stop shop, the Big Data Portal, where you can just open your browser and then go and access any of these engines from a browser. You can just write some SQL. You can just say, like, OK, run this on Spark, run this on Presto. And then it runs it, gets the data back. It's very easy to use. And the Big Data Portal depends on a Python library, the Big Data API that we built. It's just all convenience. You can just import that library in your Python application and access whatever you want in this compute platform, in this whole mess. So let's start to get more technical. Let's dive into some of these tools and technologies. And let's start with the Parquet file format. So Parquet it started several years ago as a collaboration between Cloudera and Twitter. And then the idea that Parquet implemented was not new, actually. It was just proposed by Google in their Dremel paper for assembling records for potentially deeply nested structures. And Parquet just implemented that, and then eventually it became an Apache top-level project. And then initially we were using Hadoop sequence format, and then we did some evaluation, and we saw a lot of potential in this format. Like, it brings a lot of performance improvements. So we gradually migrated into 2004 from sequence to Parquet file format. So the ideas, like I said, the ideas are not new. It's just the implementation is new. So it's a columnar format. The column data is just laid out contiguously, like the colors here. The blue one is just a layout of a single column. The other color, the purple, is layout of another column. It's different than traditional row-based layouts of relational database systems. And this layout on physical storage has a number of advantages compared to row layouts. So one thing is it provides efficient projection. So if you want to access a particular column, you just seek to the beginning of that column and do a read of a column chunk. It's pretty fast. And the other benefit is compression. So when you compress columns together, there will be similar values because you're in the same column. Let's say you have a column H, they're all integers, and since it has the values are similar, they're of type int, they tend to compress much better due to the way compression algorithms work. So you get these two nice benefits. And also there's a lot of good community support of Parquet. So all these tools that are listed here have great support for Parquet. You can just get it and work with Parquet files out of the box. And if you start zooming into the file, like get a microscope and zoom in, you will see like there are multiple row groups in a Parquet file. A row group is a collection of rows. So all your column data is laid out on disk within row groups. And every column data is in a particular column chunk. So let's say you have 3 columns. These 3 column chunks will have the raw data in your file. And then if you zoom in further, you will see like all these columnar data are split up into pages. So pages are the smallest indivisible unit of data that Parquet compress and encode. So this is what you get on disk eventually. And every file has a footer at the bottom. So it contains a lot of metadata like the schema of your file, the version information, and also you have some metadata for the row group like how many rows I have, what's the size of this data on disk, those kind of metadata. And also you get a number of column metadata like the encoding used, which encoding I am using in this file, what's the size of this column, what are the min and max in this range of values that I have in this column chunk. So this looks like useless data, but this is pretty useful when you start processing this data. For example, let's take age column again. Say you want to run a SQL query that says, give me all the people with age greater than 30. What an engine can do is look at the min max values for the age column. So in that particular file, if the maximum age is less than 30, I don't need to read that file. I can just skip forward. So you can do a lot of cool optimizations that just make use of these cool metadata here. Now, let's go a bit higher and take a look at Presto. And Presto is an open source, cool distributed system for running SQL queries in an interactive way. I think the strongest point here is interactive. That's the strongest keyword here. You can process a lot of data with traditional ANSI SQL in a cluster of machines very fast. That's what Presto does. And we evaluated Presto 2 years ago against Drill and Spark SQL at that time, and then did a number of benchmarks and evaluation, and we deployed it to production for a number of reasons that we can talk later. But we love it at Netflix because it's Hadoop friendly. If you have a Hadoop deployment in place in your production environment, if you have a Hive metastore, you can just throw Presto at your infrastructure and point Presto to your Hive metastore and then start processing data. It just integrates well with the old Hadoop tools. And it works pretty well on AWS, Amazon Web Services, because it is a very good S3 file system implementation. So you have Hive metastore, Presto points at that, get the metadata, and then you can get the data from S3 because it has a nice connector to S3. And it's pretty scalable. I mean, it's deployed in Netflix. It's deployed at Facebook where it was built. So Facebook built this system, and Facebook is running a lot of clusters of Presto. Probably more than a few hundred nodes. We are running it on a lot of, more than 200 nodes right now. It's proven to be scalable at our scale and at Facebook scale right now. And it's ANSI SQL. It doesn't, require you to learn another SQL dialect like Hive query language or, or specific dialect that you need to learn. And it's open source and it's in Java. You can just check the code out, make modifications, build it, and deploy your cluster. And finally, it's pretty fast. So this is a benchmark that we ran. It's evaluating Presto, I guess, 0.125 version, something like that, and Hive 1.0. And this is showing the query completion type for 3 different types of queries, where one is a group by query, one is a group by aggregation plus some join, and another one is a needle in a haystack, which is like scan this whole table, but give me a few rows that match this predicate, something like that. So long story short, what this shows is like, depending on your workload, your query, you can get a speed up of 4 to 5x to several orders of magnitude with Presto compared to Hive. And there are reasons for it, and the number one reason being, with Hive, when you're running on MapReduce, every stage that you have in your application just serializes all the data to disk, to HDFS, and the next stage picks it up, and which is pretty slow because when you access HDFS, it's like you do a lot of disk I/O and network I/O, and Presto gets rid of that because Presto just scans the data from S3, and everything is then in memory and streamed through the network. So it's in-memory stream processing architecture that it has, and it has plenty of optimizations in its logical optimizer, and it does a lot of bytecode generation. It's a pretty optimized piece of machinery compared to Hive. So I mentioned like we are running it on several hundred machines. So we have multiple Presto clusters right now. The ad hoc cluster is what our users are using in production. And there's a dedicated Ignite cluster powering the Ignite application that I showed at the beginning of this talk. So the ad hoc cluster is like there is a single master, single coordinator, and there is 220 machines attached to that coordinator, which are all running on R34XL EC2 instance type, which is a memory optimized instance. And this cluster, interestingly, supports elasticity. That is, you can just expand the cluster if you have workload to process or shrink it if you don't have anything to do. And similarly, the Ignite cluster is a small cluster. It's like 10 machines. It's running on a compute-optimized EC2 instance like C38XL. Again, you can just expand and shrink it based on your workload requirements. So when you want to productionize an open source system, you really need to integrate that with your tools. So this is what we do with Presto. So with Presto, what we need to do is like we need to integrate it with our systems at Netflix. So here's the Presto cluster. Here's the Presto cluster. The yellow one, the blue one is the sidecar that's running in addition to the Presto JVM. So the green one is the Presto JVMs itself. So the red one that you see here is the Presto coordinator. The others are the worker machines. So what we did is like, so whenever a query completes, we just publish that event to our data pipeline, to Kafka, and it's written to S3. So why do we do that for integration? And the reason is, when we do this, later on we can say like, okay, this query accesses this table. So this is really for data lineage, where you want to really keep track of who accesses which table. And other thing that we did to integrate Presto with our production environment is publish performance metrics to an open source system that we built called Atlas. So whenever you productionize a system, you want to really monitor it and create alerts on problems and everything. For that, you really need to integrate that particular open source software to your monitoring systems, and this is what we did here. And we publish a lot of interesting performance metrics through the sidecar JVMs to our Atlas monitoring system. And if a problem happens, like the machine went down or some queries start failing, we just get paged through PagerDuty and check these metrics on Atlas and then try to understand what was going on at that time in the production environment. And we just don't use these open source tools. We just help Facebook and collaborate with them to build all this cool stuff. And these are some of the contributions that our team made. And number one is related to Amazon file system, the S3 file system implementation in Presto. So we build all these cool features like multi-port upload support, where we do multi-threaded writes to S3 instead of doing chunk at a time. So we build support for instance credentials for security. Same for role support. It's a security concept. And also we build a lot of machinery within the file system for better reliability. We also spend a lot of time for complex type support. So the number one goal for complex type support work was bridging the gap between Hive and Presto, so that our users who want to make a switch from Hive to Presto, they just do it because we build all these nice support to complex types. We added some nice optimization rules to the query optimizer that Presto has. So we were rewriting these complex joins and distings into forms that are running much faster. Also did a lot of work with the Parquet file format, like bring support for schema evolution where column names change, column types change, those kind of stuff. And also built a cool optimized Parquet reader which can do the reads in a vectorized fashion. And finally, there's a number of other features that we built, like graceful worker shutdown, which we use for the shrink mechanism that I mentioned. So we build it so that we can drain the workload on some worker and then gracefully shut it down. And also we have built like a web connector for Tableau, business intelligence tool, and other cool features and fixes for the shell, Presto shell. Now this was the Presto part of it. So we use it for interactive SQL processing. Now let's take a look at Spark, which is sort of a new system that's out there that Databricks is pushing. And Spark is a general distributed compute engine. So in addition, I mean, when you look at Spark, comparing it to MapReduce, what we already know, it provides additional primitives. So MapReduce just provides a map and reduce functional primitives. But with Spark, you get more than that. MapReduce, and in addition to that, you get a number of other high-level primitives that you can use to construct logical plans or logical data flows. And here you see at the bottom 3 resource managers that Spark supports right now. And one is the standalone resource manager that is coming out of the box with Spark. Other one is Yarn, which is Hadoop Yarn, the yet another resource negotiator, Yarn system that's open source with Hadoop. And the other resource manager is Mesos. So Spark can run on any of these resource managers right now, and I will mention that we are running it on Yarn in a minute. And then the core part of Spark, the core module, is like there for providing all these system services like scheduling, fault tolerance, all this stuff, or implementing the core resilient distributed data set abstraction in Spark. And on top of Spark Core, people have built all these cool modules like Spark SQL for structured data processing, Spark Streaming for streaming computations, MLlib and GraphX for machine learning and graph algorithms. So this is what Spark offers. And we evaluated Spark. So we are currently running mostly Pig and Hive for MapReduce stuff, for batch analytics. And we do a lot of ETL pipelines on Pig and Hive and doing a lot of reporting and analysis on Hive engine. And we are doing right now interactive stuff with Presto, but there are two additional use cases which doesn't really fit well to Presto or Hive. And these are like, one is the iterative machine learning algorithm. So MapReduce is not designed for iterative stuff. So if you start doing iterations on MapReduce, as I mentioned previously, the next stage the stage will write data to HDFS. The next stage, in the next iteration, you will need to pick that data up from HDFS, and you do this 100 times. You are hitting HDFS 100 times, and it kills your performance. But with Spark, you can cache the data in clusters memory, and you can just iterate on that data. And that's pretty fast compared to MapReduce. And another use case is like we need good, flexible APIs for some custom programmatic use cases that we have. With Hive or Pig, you are limited to the language that they provide. Like you are limited to the Pig Latin language or Hive query language. But with Spark, it gives you a cool Scala API that you can construct very complex data flows easily. So there are currently 2 Spark deployments at Netflix. One is Spark on Mesos that some other team is managing and doing some stream analytics on top of it. But what we do in the big data platform is we are running Spark on Yarn because we already have a Yarn cluster of several thousand nodes. We just want to use the same cluster, same piece of hardware to run our Spark jobs too. So we are running Yarn on Amazon's Elastic MapReduce service. And currently we just started doing some batch analytics and doing some ETL stuff. And an interesting thing that we do in our Spark deployment is like we provide support for multiple versions. So what this means is like a user can, from a bash CLI, can just say like, okay, give me a Spark shell with version 1.5. So you can think like multi-version support can be useful, in a number of ways. Like for example, if you have 3 deployments, 3 versions, like 1.4, 1.5, 1.6 that you can support, if you hit a bug in 1.4, it may be fixed in 1.5, so you can just point to that new version and get the fix. Or if there's a new feature is available in 1.6, you can just point to that and experiment with that feature. So the core system that provides multi-version support is this tool that I mentioned, like Genie, which is a federated execution service. And what it provides in this whole thing, multi-version support thing, is you can configure Genie to have multiple applications, like multiple Spark binaries, and then point those binaries to multiple configuration files. Like, okay, for Spark 1.6, use this set of configuration files. Spark 1.5, use this set of configuration files. And whenever the user asks for, give me Spark 1.5, it downloads the related binaries, related configs, creates a nice sandbox for your job, and kicks it off to the Yarn cluster. And in addition to the multi-version support, there's a very important concept that we deeply care about, which is multi-tenancy. So this is a graph from one of our monitoring tools. And what this shows is like, we are running, the blue ones are like the MapReduce containers that are running in our infrastructure in this Hadoop cluster. And the yellow containers are the Spark tasks that are running in this infrastructure. So we are trying to run multiple workloads on the same hardware, and this is called multi-tenancy. And what this brings you is cost and resource efficiency. You have these machines there sitting idle. Instead of letting them sit idle, you just pack the workloads you have, and they are at the same time. When you look at a machine in our cluster, you will see like they are running both map and reduce task and Spark containers at the same time in the same box. And to provide multi-tenancy, Spark has a very interesting feature called dynamic allocation. And before talking about dynamic allocation and our experience with dynamic allocation, I will just recap the task execution model a bit here. So with Spark, so you have all these tasks from your application. What Spark does during runtime is grab some containers from the Yarn cluster, the resource manager, and then start submitting those tasks to those containers. And these JVMs, the executors, are separate Java processes, JVMs. And then these tasks are dispatched to these JVMs, and the JVMs processes these tasks in separate threads. So the main thing is like the executors are persistent during the runtime. But with MapReduce, what was happening is you have these tasks again, the map and reduce tasks. And for each task in your application, MapReduce was just grabbing another JVM. So for every task, you have another JVM that's running that task. So the model is different a bit. So the JVMs are temporary. They are just recycled when the task is finished. But with Spark, the JVMs are staying there when the task is finished. So what dynamic allocation does is, whenever there are pending tasks in your queue while you are running your application, Spark looks at this pending task queue, and then if there are tasks to process, it just asks the Yarn resource manager to grab more containers during runtime. And then so it is really expanding your cluster, your resources during runtime if you have workload to process. And when your tasks start finishing, it just shrinks the cluster back. So this is what dynamic allocation does. And it just starts slowly when your application starts, and then gradually expands the number of containers that you get, number of JVMs that you get. And then when they start staying idle for some time, it just starts releasing them so that other people can use. And like I said, this is good for multi-tenancy because whenever you need, you acquire all these resources. Whenever you don't need them, you release them so that other people, like other MapReduce applications, can use those resources. And it helps you utilize this cluster resources better because whenever there are idle resources sitting around, you just grab them and then send some Spark tasks on them. And similarly, it's really good for interactive applications. Like if you have a Spark shell open, interacting with the cluster right in front of your monitor. So what happens is like if you submit a job, it starts expanding so that you can start grabbing the resources. So you get this interactivity immediately when you start processing your job. Now I will start talking about our dynamic allocation experience. We deployed this dynamic allocation logic in our Yarn cluster, and we started running it on several hundred containers at the same time. So we have this huge cluster of a few thousand machines, and every user can allocate up to 500 containers max. So we deployed this to production, and we started having problems immediately. So I'll just recap some of the problems that we hit and solved, so that if you hit them, these look familiar to you. So the first problem that we hit with dynamic allocation on Yarn is the poor performance of broadcast variables. So what a broadcast variable means is if you do a broadcast join or if you create a broadcast variable, what it does is it creates a copy of this data, and then it sends that copy over the executors, over the workers. So this read-only copy is distributed in a torrent-like protocol. So you have this data is chunked up, distributed. So all the executors replicate this. So during runtime, if an executor requires that data, it just fetches those blocks from a remote executor and then just does its processing. And the problem is, when you use dynamic allocation, the replicas may be removed, because if an executor stays idle, it will be removed. And this causes some problems. Here you see some logs here at the bottom, and you see like a worker has done 70 failed attempts in more than 17 minutes, 17 minutes, 17 minutes to just grab a small block of data. And then we solved this, and what the hell is going on here? 17 minutes to fetch a few kilobytes of data. So we started digging in to try to understand what's going on here. And then what we found is, so this particular executor, so the executor gets a list of locations from the driver. so that it will just go and fetch these replicas. And then due to dynamic allocation, many of the executors in this location list, the replica list, may be stale. Because if you do a lot of big dynamic allocation and release, this location list can have a lot of stale entries. So this executor get like more than 70 stale entries and started pinging them one by one. And every failure, because that executor removed, caused the retries to kick in. And we have like 3 retries with 5-second gaps. So this means a single attempt is like 15 seconds, and you do this 70 times. If you do the math, you will get 17 minutes. So it's just executors are removed, the executors are removed, and the receiving side just sees that those are live because of the staleness. And the fix was pretty easy, actually. What we did is like, if an executor hits multiple failures, it just refreshes the locations from the driver. So the time to conversions, time to fetch a broadcast variable just falls from 17 minutes to a few minutes at most. So another problem that we have with dynamic allocation is a broken locality optimization. And what was happening is like, so there was this optimization built into the dynamic allocation module. And the optimization is to optimize locality. So if you want to send a task to some machine, so if the data is on that machine, you can just do a local read instead of reading it remotely. So this is called locality. And to optimize locality, what dynamic allocation module did was, if there is a number of pending container requests, so the dynamic allocation module was just canceling many of these requests, so that if it cancels and resubmits those, in the meantime, hopefully some of the machines free up that you need, so that you can lend some of the tasks to these machines, and then hopefully get data local execution. And what we figure out is like, this didn't play well with S3, because with S3 we didn't have any locality at all. Like, all the data is removed on S3, so whether you try to optimize locality or not, you get no locality at all. It's just removed trees all over the place. So what we did was simply, for S3 requests, just don't cancel and try to do this optimization. And another thing that we hit, another problem that we hit, was with cache data sets. And then the problem is, so like I said, with Spark you can cache data set, you can iterate on them, you can do all kind of cool stuff. And then what we noticed is like, if you cache the data with this code snippet here, when you call persist and count, you will see like the data is brought into cluster memory. We saw like when an executor is removed that contains cache data, so your job will fail, because the cache data is gone, and when you try to access it, you won't be able to find it, and then the application will just fail. So the solution was out there and simple. So with the default dynamic allocation mechanism, if an executor is staying idle for some time, you just remove it. But with cached executors, with cached data, you just define a new timeout, and then with that timeout is typically set to a longer value. Like in production, we set the default value to 1 minute, but for cached data, we set it to 15 minutes. So hopefully, you reduce the likelihood of failures due to cached data. So we have made a number of other contributions, all this stuff. I won't go into details, but we have fixed a lot of problems with Spark to productionize, and we'll talk about it later in our other conferences. So if you're interested in this stuff, just come talk to me after the talk, we can chat. So what's next for us, all this cool stuff that we thought, like Presto, Spark, Hadoop, Hive. So what's next for our infrastructure is, so we want to get, of course, better performance. There's always room for performance optimizations in Parquet and Presto, all this stuff. Like, for example, you can, using the metadata again in Parquet, you can check the dictionary if you are using dictionary encoding. Using that dictionary, you can just skip, again, a number of, columns and skip a lot of I/O. So that's one thing that we plan to look at in the near future. And another thing that we want in our platform is better visibility. So we want to really understand what's going on, so that if something breaks, we can just dive in. So currently we have some visibility with Presto, like with Atlas metrics, but with Spark we are still, integrating it with our production environment. So we want to get more metrics to our Spark infrastructure. And finally, we would like to explore new use cases. Like so far we looked at, with Presto, we looked at interactive stuff. With Spark, we looked at ETL, some interactive. But going forward, we would like to interest other stuff like reporting, data validations, or ETL on Spark a little bit more. So we want to explore these new use cases and try to identify where these different engines can help us in all these different use cases. So I guess the key takeaways that I want you guys to take home is like, first of all, there is a reason why we use all these tools in our production. So we don't just stick to one tool. We just deploy many tools, and we don't do it for fun. We do it for a reason, because you need to really use the right tool for the right job. You cannot really do interactive processing on Pig or Hive, or you cannot do the flexible custom data flows on Pig. You need to use Spark for that. So there is a reason we deploy all these interesting systems here. So use the right tool for the right job. And the second thing is, we are a company that really cares about open source. We just don't use the systems that are open source there. We use them, we fix them, we contribute new features, we let the tools scale up, scale out to our, distributed infrastructure so that other people can benefit. So what this ends up in, like, you can just go, check out these systems and deploy whatever we have in production to your own infrastructure. So whatever we build is just out there. You can just build it for yourself too. And finally, Netflix is one of the, I guess, biggest, or if not the, the biggest one, using the Amazon Web Services infrastructure. So everything we have is on cloud. So we are 100% cloud right now. And there are a number of advantages there, right? You don't need to really, build this machinery to deploy your software. You don't need to build all these cool services that Amazon provides. You just pay for what you use, and you just need to use them to build your distributed infrastructure. So everything is there. Just use it. You don't need to spend time thinking about all this infrastructure stuff. Amazon has done, much of this stuff for you already. So we have been through all this stuff like Presto, Spark, Parquet, all these cool technologies that we are using in production. And I mentioned some of the details and some of the use cases that we use those for. And if you want to learn more about this stuff, so I think the first thing you should do is like go to our engineering tech blog. So we have a number of blog posts there that mention a lot more details than this talk. And also we will be giving a lot of talks around this summer. Like if you're interested about Spark stuff, where most people are interested in. So we'll be giving some talks in Hadoop Summit and Spark Summit this year. So we will talk about how we productionize Spark for ETL, how we do it, what kind of problems we hit. In addition to some of these problems that we hit there, we will mention a lot of experience that we get on the road. And also, so I would like to, again, thank you all for attending this. Hopefully you get a glimpse of what we are running in production and some of our experiences we had with these tools. And I'd like to thank you all again for coming, and I'll be happy to take any questions you guys may have. Thanks, guys. Questions? Any question about anything?
Can you give some detailed information about your Kafka cluster? For instance, how many nodes do you have in that cluster?
So the Kafka cluster is maintained by a data pipeline. It's a separate team. It's a data pipeline team. So what I know is like they are running multiple clusters of potentially up to several hundred nodes. So it's a very big multi-cluster deployment that's processing, like I said, 600 billion events a day. It's a pretty big deployment. In total, yes. In total, there are several hundred nodes in total. This Kafka is running on, yeah. Yeah.
I think default SQL context in Spark is high.
Yes.
Can we use another, for example, Presto as a SQL context in Spark?
Not that I am aware of. There is no system out there that integrates the two. But what I know is like Spark provides an ANSI SQL context too. There is some support for ANSI SQL, but it's very limited. It's almost useless. So if you want to do some serious SQL stuff, either you will use Hive on Spark, but then if you want to do ANSI SQL, I guess you don't have much choice. You need to go to Presto or some other tool. Yeah. Yeah, that's a good and a tough question. So the question is, how do you decide what tool is the right for you? So So to decide that, first of all, you need to understand your use case, and you need to get some requirements. You need to gather some requirements. So like, for example, for Presto, let me give you an example about how we chose Presto. So we wanted to have an interactive execution engine because we have these interactive use cases where analysts just want to get some results in seconds. And we had a number of candidates, like we have Drill from Mapr, Spark SQL from Databricks. We looked at Impala from Cloudera, and we have Presto from Facebook. So we collected the requirements. It's like good performance, and then good integration with Amazon, because we are running on Amazon. We don't want to build the whole machinery to integrate it. We want a quick solution. So good integration with Amazon, good stability, because whatever we are running on, we will run it on several hundred machines. It won't be a toy deployment. So whenever you deploy any of these production systems to 100 machines, they just break. So we want some good stability. So we did some evaluation across all these tools, and then we started crossing them. For example, with Drill, we had some stability problems on several hundred machines. We just crossed it off the list. With Impala, it didn't have any S3 support, so we just crossed it off the list. And it was written in C++, so we didn't want to spend another year to write a S3 file system for Drill in C++, so we just crossed it off the list. So we looked at Spark SQL, and then we hit some performance problems, so it wasn't as interactive as advertised. So the performance that we get was very poor. It was like smaller queries was taking several tens of seconds to minutes. But when we evaluated with Presto, what we saw, like, it was pretty reliable at scale. So we have this S3 file system out of the box, and then the performance was like most of the queries was taking a few seconds compared to all these other engines. So it was just a no-brainer to take the decision. So you should really understand your use cases. You should benchmark it yourself with your data on your hardware, your performance metrics, and then you need to do this across a number of tools and take a decision. Yeah.
Can you give us a brief information about your
Transaction management. So currently we do not do any transactions. So you mean like distributed transactions, how we manage those, like the consistency and performance, those kind of stuff. So we don't run distributed transactions at all. So these are all NoSQL stuff. These are just independent. These frameworks are like processing independent tasks. So there are no locking, no consistency issues. They are just embarrassingly parallel computations. So we don't do any transactions at all at this part of the infrastructure. Yeah.
What's your next step of scale data platform?
So the next step, like I said, so to scale it up. So first of all, we need to understand whether we should scale it up or out. So to understand that, we usually monitor our workloads and the latencies and everything. If we think like the infrastructure is not capable of handling all these workloads, so we scale it out. So that's how we scale it out. But so the next step is usually like we look at the new use cases. If there's a new use case that really requires us to scale the infrastructure out to provide better performance, to provide lower latency. For example, recently we have been seeing like our ETL workload is pegging one of our Hadoop clusters. So we think like, okay, the right thing to do is probably either optimize these jobs, we do some optimizations to use less resources, or if we cannot do anything else, we just deploy, rent more resources from Amazon EC2 and then, enlarge the cluster, or use dynamic allocation or auto expand and shrink to gather more resources when there is more workload to process. So these are usually the things that we do to scale out our systems.
Because why I ask this question? Because I know that General Electric is built a predicts environment, and they are going to make some big data problems. They are going to solve them. So do you have any chance to look at kind of solutions? Or
so can you repeat the first part? What kind of solutions are you talking about?
predicts environment. Do you have any idea about that?
No.
No. Okay.
Is it open source?
No, it's a General Electric's platform. They are also looking for that kind of problems, analytics scale.
No, I'm not aware of that. No, we are not looking at it right now. Any other?
How we are giving the decision that at the end of an evaluation on Spark or on any platform, that's the right end for the solution?
So you collect data. I mean, you have these requirements, like I mentioned, Presto versus Spark. So you get your data, and our metric was, like I said, reliability and performance. I look at those metrics. I mean, if one performs obviously better than the other, you go for it. If you see like you don't get much difference between the metrics, you know, the system seem like on par for your use cases, then I would probably go for the developer community, how active it is, how well the code is written, you know, how the open source project is maintained, is it open or is it a closed, you know, closed community of people, you know, managing the project. There are other software development aspects to it, but for the most part, you just collect the data and, you know, try to understand how it will behave for your use cases.
I'm not asking for the tools, but for the data analyst part. How you are ending with the right solution at the end. How you are deciding it.
Deciding what?
After analyzing some data, you give a decision. How you are sure that that's the right one?
So it's statistics then. I mean, the analysts, like for example, for those A/B testing stuff, so they want to take a decision, right? They run experiments, and those experiments, in the end, when they analyze the results, they create some statistical metrics. There is a lot of statistical theory there that gives you some confidence for the results. So if you make a change and you get a good confidence as a result of your statistical analysis, you can say that, okay, with 90% probability, 90% confidence, my solution is correct. So you cannot get 100% confidence. You just see like, this is probably on average, you know, most of the time this is correct, so you go that way. I mean, if you make a mistake, you can always revert it, so it's not like the end of the world. But statistical tools help you take a good decision most of the time.
Do you suggest Druid to quick start big data?
Druid. So there are some teams using Druid. So what I know about Druid is I'm not that familiar. Drill, okay. So you want, okay, Drill. So the last time that we checked Drill, it has a lot of problems in terms of stability issues. But recently they have just released 1.0 and they are making it more stable. The mapper is spending a lot of time on that. So after the 1.0 release, we didn't do any evaluation, but I guess it's getting much better. And I'm seeing like some benchmarks around that's showing it has good performance. So you can just do a benchmark and see how it behaves for your case.
Because it is schemaless design, I think.
Schemaless, yeah.
Hive is required schema definition.
Yeah, the drill is discovering the schema itself under the hood. With Hive, yeah, you need to define the schema of your tables. And the tools just discover that schema and do this schema evaluation on read and do the processing. I mean, both ways have its, you know, advantages and disadvantages. You know, with schemaless, you just point to the data and it discovers it and you do the processing. But with the schema support, it's also more verbose and explicit. So it gives you a lot of info, and the engines can use those schema to make better optimizations. So both parts of the world have advantages and disadvantages. Any other? Yeah. Spark streaming, yeah. We do not have a Spark streaming deployment in our platform, but there are some teams using it. And there is a blog post on Netflix Engineering Tech blog. If you search for that, they mention a lot of details there that I'm not familiar with because it's some other team that's doing that. Any other comments, questions? I guess that's it. So if you have any other questions, I'll be around for the next hour or so. Just catch me. Thank you, guys.